Oh, sorry, the workbook pages were 189 all the way to 204, and we've been looking and dealing with those circle notes for a good long while. We are discussing three scenarios. Three different scenarios in the back of you. One involves two chords intersecting inside the triangle. Now inside the circle. Now we've seen this happen before when two chords are intersecting, but we've looked at the angle measurements and the intersected arcs. And we said that, well, if the vertex is inside, then that angle measurement is 1/2 the sum of those two intersected arcs. So we've dealt with this diagram, this type of situation before, but we were looking at the angle measurements and arc measurements. Now, we're turning focus to looking at the lengths of these segments. So when this happens, when two chords intersect inside a circle, each chord is broken up into how many parts? 2 parts, okay? So there are 4 pieces in the end. This point of intersection creates these 4 pieces. And the proof right above this on your notes proves that when this happens, if I were to draw some auxiliary segments here, we can prove, what we're not going to do right now, but we can prove that these two triangles are similar. I know that this angle is congruent to that angle. Why? Vertical angles are always congruent. Okay? Then, this angle in this triangle right here is congruent to that angle there. Can someone tell me why? What's up, Kyle?
Is it because they share the same arc?
They intercept the same arc. Good. So check it out. This guy right here is opening up to this intersected arc. Well, this guy is also opening up to that arc. So yes, those two angles are congruent because they intercept the same exact arc. We've proven that these triangles have 2 congruent angles. If that's the case, can we say anything about these 2 triangles? They're similar. By what theorem? Angle, similarity. If 2 triangles are similar, their angles are congruent. So we've proven that their angles are congruent. But what's true about their sides? They're proportional. Good, Sam. They're proportional. So we can set up a proportion. Now, identifying the corresponding sides, we need to look at and use our angles. Because I know that this angle is congruent to that angle as well because they intercept the same arc. So we know all of these angles are congruent. So when we set up a proportion, we need to make sure that we're comparing the correct sides. Now, the length of this green segment is 2x. The length of this blue segment is 12. If I'm wrong, tell me, because it's being projected, it's kind of blurry. And then the length of this red segment is 15, and the length of this segment, we got a big old arrow drawn over, and that is x plus 3, correct? All right, cool. What happens is we can set up a proportion because sides are proportional in similar triangles. So, do you see how the green segment is formed by an angle with 1 mark of congruency and an angle with 2 marks of congruency? Do you see that? Okay? So that side, 2x, is going to correspond with, I'm going to put it below the red segment because it's formed by the angle with 1 mark of congruency and 2 marks of congruency in that other triangle. Are you smelling what I'm stepping in?
Yeah.
Are we okay? Alright, so I'm just comparing the corresponding parts, but I'm using the congruent angles to help me identify those corresponding sides. Now we need to do the same thing over here. I started off with a length from this smaller triangle down here, so we need to stay consistent. So I've got x plus 3 is going to be up on top, because these values are coming from the same triangle. Well, that side is formed by the angle with 1 mark frequency and 3. So that's corresponding with the blue guy. Because in this other triangle, it's being formed, or it's in between the angle with 1 mark frequency and 3. I can set up this proportion. I can set up this proportion because I know the sides are proportional. So let's take the cross product like we always do. So I got 2x times 12 and that equals 15, and we've got times x plus 3. Please tell me we haven't talked about this already. Okay. For some reason, I just have this deja vu, like, oh, we've already been through this. Okay. Let's say this is just a waste of time. Now, so we just took the cross product. That's all we did. Rather than going through that nonsense every single time, it's a theorem that this is going to happen every time, that the triangles are similar, the sides are proportional. And so in the end, what we've got is because these triangles are similar, we took the product of the two pieces of one chord. Okay? This is one chord right here. It's been broken up into two pieces. And we ended up taking the product of those two pieces. We took 2x and we multiplied it to 12. Product of the pieces. You feeling okay still? And then that will equal, well, right after we did the cross product, we got the product of the other pieces, because this is a whole chord, it's being broken up into two pieces. So we did the product of those pieces. This is a theorem. And so if you look at the very, very top right of your piece of paper, in that rectangular box, it is very, very, very wordy what it says in that top box. This is what it says. Theorem, when two chords intersect in a circle, just like this. Two chords intersect in a circle. This is what your textbook would say. The product of the lengths of the segments of one chord equals the product of the lengths of the segments of the other. So what we're going to say is, hey, when this happens, when two chords intersect in a circle, the product of the two pieces is going to equal the product of the two pieces. And so that's a theorem. Somewhat we just proved this by using similarity, so we don't have to go through that nonsense every single time. So when you have two chords that are intersecting in a circle, you take the product of their pieces and you set those two things equal to one another. Whenever you have an expression, a binomial like this, x plus 3, as one of the lengths of the pieces, you need to put it in its own set of parentheses. Parentheses are your friends. And so when you have a binomial, that means a polynomial two terms like this, put it in its own set of parentheses. Because now that I have done that, now that I see that this is a binomial and I put it in parentheses, how am I going to take the product of 15 and x plus 3? What am I going to have to do? Yeah, I have to distribute. But it's difficult to see that if you don't get in the habit of putting that expression in its own set of parentheses. Okay? Looking at those workbook pages that you should have out, go to page 199. Go to page 199. We're going to do the odds on this page. The odds. So number 1, number 3, and number 5. Number 1, number 3, number 5 is just like this problem. You've got two chords intersecting. Product of the pieces equals product of the pieces. Okay? However, 7, 9, 11, 13, and 15, the other odds on that page, we still need to discuss. Those diagrams are like the other two scenarios over here to the right. Now, you notice with these scenarios, there is a portion of the segment that's outside of the circle. You see that? Okay, so can anyone tell me what this type of segment's called in our circular vocabulary? Like, is that a diameter? Is that a radius? It's a secant, because it has 2 points of intersection. Who can tell me what this guy is? So this is a tangent, okay, because it has 1 point of intersection. Whenever you have secants or a combination of secants and tangents, we're going to follow the rule. And again, it's because we can find two triangles that are similar. Because this is what happens. You've got a triangle here, and then you've got another triangle here. We can prove that they're similar. Because they are, by angle, angle. But we're going to follow that we're going to take the outside length, which in this case is 4, and we're going to multiply that to the whole length of this secant segment. What's the whole length? 9. Just using a little bit of segment addition postulate. Part plus part equals whole. And then we're going to look at the other secant segment. The outside portion is x minus 2. And then the whole length is where we add these two values together, combine like terms. I've got x minus 2, and I'm going to add that to the portion that's on the inside, x plus 4. I'm trying to get the whole length. How many x's do I have when I add these? 2. So 2x, and then negative 2 and positive 4. When I combine that, what do I get? Positive 2. And because similar triangles are formed, what we do is we take the outside portion and we multiply it to the whole. So in this case it would be 4 times 9. Outside times whole. And that's always going to equal, looking at the other secant segment, that's always going to equal, same rule, outside, which is x minus 2 for that guy, times the whole, which is 2x plus 2. These will always equal. So when you got tangents, or we got secants, there's a portion outside, it's outside times whole equals outside times whole. That's all written for you down below here in that box. That's all written down for you in the box. Check out the tangent. What's the outside length of this guy right here? What's the outside?